Hello and welcome to Space Historians. I am glad you have joined me, ready to slow down, breathe deeply, and let your thoughts drift weightlessly beyond our world. This is your moment to leave the noise of the day behind and step quietly into the vast, starlit corridors of cosmic history. Each episode here is not just about stars, it is about the stories they hold, the forces that shape them, and the quiet mysteries still waiting. If you enjoy these quiet journeys, a like and a subscribe help keep this channel orbiting. But for now, you do not need to do anything but listen. Somewhere in the universe, right now, something is happening that releases more energy in 10 seconds than our sun will emit in its entire 10 billion year lifetime. Not in a year, not in a century, in its entire existence. The energy released is so immense that if you could somehow capture it and convert it to matter using Einstein's famous equation, you could build thousands of stars from scratch. This is not science fiction. This is not exaggeration. This is a gamma-ray burst, one of the most violent events known to physics, and it is real. The first gamma-ray burst was detected by accident in 1967, not by astronomers searching the sky, but by military satellites designed to monitor nuclear weapons tests. The sensors picked up flashes of gamma rays, the highest energy form of light, coming not from Earth but from space. At first, the data was classified, kept secret for years. When it was finally released to the scientific community, astronomers were baffled. What could produce such intense bursts of the most energetic radiation known? The signals lasted only seconds, sometimes less, and they came from random directions across the sky. For decades, the origin remained a mystery. Were they nearby or distant? Were they from our galaxy or beyond? Every theory seemed to require physics pushed to impossible extremes. Some proposed colliding neutron stars. Others imagined exploding black holes or stars being torn apart by gravitational forces. The problem was that without knowing the distance, astronomers could not calculate the true energy involved. A flash from across the galaxy would be impressive. A flash from across the universe would be beyond comprehension. The answer came in 1997, when astronomers finally measured the distance to a gamma-ray burst. It was not in our galaxy. It was not even in a nearby galaxy. It was billions of light years away, so far that its light had travelled for most of the age of the universe to reach us. And yet, even across that immense gulf, it was bright enough to be detected. The implications were staggering. To shine that brightly from that far away, the burst must have released more energy in seconds than an entire galaxy of hundreds of billions of stars produces in the same time. This realization marked a turning point. Gamma-ray bursts were not just mysterious flashes. They were among the most powerful explosions in the universe, second only perhaps to the Big Bang itself. They represented destruction on a scale that dwarfed everything else we knew. A supernova, the death of a massive star, releases enormous energy, enough to outshine its host galaxy for weeks. But a gamma-ray burst in its brief eruption can release 100 times more energy, concentrated into two narrow beams of radiation that slice through space like cosmic searchlights. To understand what this means, imagine standing on a planet orbiting a star 10,000 light-years from a gamma-ray burst. Even from that distance, if one of the beams happened to point in your direction, the burst would appear brighter than the sun in your sky, not for years, but for seconds. The radiation would strip away your planet's atmosphere in moments. The ozone layer would vanish. The surface would be bathed in lethal gamma rays and X-rays. Any life, no matter how resilient, would be sterilized instantly. The oceans might begin to boil. The sky would glow with the ionization of the air. And then, just as suddenly, it would be over, leaving behind a dead world. This is destruction on a scale that challenges imagination, not because it is exotic or theoretical, but because it is so absolute. A gamma-ray burst does not merely damage, it obliterates. It does not leave ruins. It leaves nothing recognizable behind. And yet, these events happen regularly across the universe. roughly once per day somewhere in the observable cosmos. We do not see most of them because their beams point away from us, sweeping through empty space, missing Earth by vast angles. But occasionally, one points our way, and we catch a glimpse of the violence. The question that opens this journey is simple but profound. What is the most destructive thing in the universe? Is it gamma-ray bursts with their unimaginable power and lethal beams? Is it black holes, which trap everything that falls too close, crushing matter to infinite density? Is it supernovae, the deaths of massive stars that scatter elements and energy across light years? Or is it something else entirely, something we have not yet fully understood, lurking in the shadows of cosmic violence? To answer this question, we must first define what we mean by destruction. Is it the amount of energy released? Is it the radius of devastation? Is it the permanence of the damage? Is it the ability to erase information itself? Each measure points toward different candidates, and as we move through this exploration, we will see that destruction is not a single concept, but a spectrum, with different phenomena occupying different extremes. Gamma-ray bursts represent one extreme. They are the most energetic explosions known, concentrating the power of countless stars into beams narrower than a degree across. But they are brief, lasting only seconds, and their beams are focused, leaving most of the surrounding space untouched. Black holes represent another, extreme. They do not explode or burst. They consume, slowly and relentlessly, trapping everything within their event horizons and holding it forever. They can grow over billions of years, eventually dominating entire galaxies. Supernovae occupy yet another position. They are less energetic than gamma-ray bursts, but more widespread in their effects. They scatter enriched material across space, triggering new star formation, even as they destroy old stars. They are creative in their destruction, builders as much as annihilators. And then there are rarer possibilities. Quasars, powered by supermassive black holes that shine brighter than entire galaxies for millions of years, colliding galaxies that reshape hundreds of billions of stars through gravitational chaos. Even the slow expansion of the universe itself, which will eventually tear apart every structure, every atom, given enough time. This is the impossible beginning. The recognition that the universe contains violence on scales so vast they defy everyday understanding. These are not human-scale disasters, they are cosmic catastrophes, events that operate across light years and eons, reshaping the very fabric of space and time. And yet, for all their power, they are also natural, predictable, governed by the same laws of physics that describe falling apples and orbiting planets. The universe is not malicious, it is simply indifferent, and in its indifference, it permits extremes. As we step into this story, we carry with us a question that has no easy answer. What is the most destructive thing in the universe? The answer will require us to travel through time and space, to examine the deaths of stars, the collisions of black holes, the beams of gamma rays, and the slow, patient work of gravity. It will ask us to weigh energy against permanence, violence against reach, and annihilation against transformation. And in the end, it may reveal that destruction is not the opposite of creation, but its necessary partner, the force that clears the way for new worlds, new stars, and new possibilities. To understand cosmic destruction, we must first understand the stage on which it unfolds. The universe is not a small place. It is not even a large place by human standards. It is vast beyond comprehension, stretching across at least 93 billion light-years in diameter, filled with hundreds of billions of galaxies, each containing hundreds of billions of stars. Within this immensity, destruction happens everywhere, constantly, on scales that range from the microscopic to the galactic. The setting for the most destructive things in the universe is, quite simply, everywhere. The story begins 13.8 billion years ago with the Big Bang itself, the ultimate act of creation and destruction combined. In the first moments, The universe was unimaginably hot and dense, filled with energy that gradually cooled and condensed into particles, then atoms, then the first structures. Even in those early moments, the seeds of destruction were planted. Gravity, the force that would build galaxies and stars, was also the force that would tear them apart, crush them into black holes, and eventually dominate the fate of everything. The first stars formed roughly 100 million years after the Big Bang, coalescing from clouds of hydrogen and helium in regions where matter had gathered more densely. These early stars were different from the ones we see today. They were massive, often 100 times the mass of our Sun or more, burning ferociously and living only a few million years before exploding in supernovae. These explosions were among the first truly destructive events in cosmic history, scattering the newly forged elements, carbon, oxygen, iron across space, and seeding the gas clouds from which later generations of stars would form. As the universe evolved, galaxies began to take shape, drawn together by gravity into clusters and superclusters, separated by vast voids where almost nothing existed. Within these galaxies, stars formed, lived, and died in cycles that continue to this day. The setting became more complex, more structured, but also more violent. Galaxies collided, their stars flung into new orbits, their central black holes merging in catastrophic events. Supernovae exploded, gamma-ray bursts flashed across the cosmos, and quasars blazed from the centers of distant galaxies, powered by black holes consuming entire star systems. Today, the universe is a mature but still dynamic place. It is no longer the chaotic furnace of its youth, but neither is it quiet. Every second, somewhere in the observable universe, a star explodes. Every day, a gamma-ray burst erupts, sending beams of radiation across billions of light years. Every few minutes, two black holes or neutron stars collide, releasing gravitational waves that ripple through space-time. The setting is one of constant transformation, where matter and energy shift between forms, where structure arises and collapses, where creation and destruction are inseparable. Our own galaxy, the Milky Way, is part of this story. It is a barred spiral galaxy, about 100,000 light-years across, containing between 200 and 400 billion stars. At its center sits a supermassive black hole, Sagittarius A star, with a mass of over 4 million times that of our Sun. This black hole is relatively quiet now, but it has not always been so. Billions of years ago, it may have been an active galactic nucleus, devouring stars and gas, shining brightly as a quasar. Even today, it occasionally consumes material, flaring in X-rays as matter spirals inward toward the event horizon. Within the Milky Way, the cycle of stellar life and death continues. Massive stars forming dense molecular clouds, regions where gas and dust gather thickly enough for gravity to take hold. These stars burn bright and fast, fusing hydrogen into helium, helium into heavier elements, building up cores of iron that cannot fuse further. When fusion stops, gravity wins and the core collapses. The resulting rebound sends shock waves through the outer layers, triggering a supernova that can briefly outshine the entire galaxy. The remnants of these explosions, neutron stars or black holes, remain silent monuments to destruction. The setting also includes the vast spaces between galaxies, regions that are not truly empty but filled with the intergalactic medium, a thin gas of hydrogen and helium enriched with heavier elements from ancient supernovae. Cosmic rays, high-energy particles accelerated by violent events, stream through these voids, travelling at nearly the speed of light. Gamma-ray bursts, when they occur, send radiation across these empty regions, their light travelling for billions of years before reaching telescopes on Earth. Distance plays a crucial role in the setting. The universe is so large that light itself takes billions of years to cross it. When we observe a gamma-ray burst from 10 billion light-years away, we are seeing it as it was 10 billion years ago, when the universe was less than half its current age. The stars that produced it are long gone, their remnants scattered or merged into new structures. The setting, then, is not just spatial but temporal. Destruction unfolds across time as well as space, and what we observe today is always a record of the past. The expansion of the universe adds another layer. Galaxies are moving away from each other, not because they are travelling through space, but because space itself is expanding. This expansion means that the most distant objects are receding faster than the speed of light, carried by the stretching of space-time. In the far future, this expansion will accelerate, driven by dark energy, until galaxies beyond our local group disappear beyond a cosmic horizon. The setting is not static. It is dynamic, evolving, and in its evolution, it creates new opportunities for both creation and destruction. Our solar system sits in a relatively quiet region of the Milky Way, about 26,000 light-years from the galactic center, in a spiral arm known as the Orion Spur. This location is fortunate. We are far enough from the center to avoid the dangers of crowded star fields, frequent supernovae, and the influence of the supermassive black hole. We are not in a region where massive stars form and die rapidly. Our Sun is a modest, middle-aged star, stable and long-lived, allowing life on Earth to develop over billions of years without catastrophic interruptions. But even here, the signs of past destruction are visible. The heavy elements in our bodies, the iron in our blood, the calcium in our bones, were forged in supernovae billions of years ago. The gold in jewelry, the uranium in rocks, were created in neutron star collisions. We are made of stardust, but that dust was scattered by violence, by explosions and collisions that destroyed the stars, that made it. The setting includes not just the present, but the legacy of the past, the accumulated effects of destruction across cosmic history. The universe is a stage where destruction plays out in endless variety, from the smallest scales, where particles annihilate in bursts of energy, to the largest, where galaxies collide and black holes merge. The theme is constant. Structure arises, persists for a time, and then collapses or transforms. Stars burn, explode, and leave behind remnants. Black holes grow, consuming matter and merging with others. Gamma-ray bursts erupt, sterilizing regions of space. And through it all, the universe continues, indifferent, governed by laws that permit both creation and annihilation. The setting is vast, ancient, and dynamic. It is a place where light takes billions of years to travel, where energies beyond human comprehension are released in seconds, where the most violent events in history unfold silently in the vacuum of space. To understand the most destructive thing in the universe, we must first appreciate this setting, this cosmic arena where destruction is not an anomaly but a fundamental process. It is here, across galaxies and eons, that we will search for the ultimate expression of cosmic violence. The discovery of cosmic destruction did not come all at once. It unfolded gradually, piece by piece, as astronomers developed new tools and new ways of seeing. For most of human history, the night sky appeared calm and unchanging. The stars seemed fixed in their positions, eternal and serene. Comets and meteors were noted as curiosities, but the deeper violence of the cosmos remained hidden. It was only in the 20th century, as telescopes grew more powerful and new forms of observation emerged, that the true scale of cosmic destruction began to reveal itself. The first hints came from supernovae. These stellar explosions had been recorded for centuries, appearing as new stars that flared brightly and then faded. Ancient Chinese astronomers documented several, including the supernova of 1054 that created the Crab Nebula. But without understanding what stars were or how they worked, these events remained mysterious. It was not until the early 1900s, when astronomers began to study other galaxies, that the true power of supernovae became clear. In 1985, a supernova appeared in the Andromeda Galaxy, our nearest large neighbour. It was bright enough to be seen with modest telescopes, and it prompted astronomers to search for similar events in other galaxies. They found many. Supernovae were not rare flukes, but regular occurrences, happening roughly once per century in any given galaxy. As the distances to these galaxies became better known, the energies involved became calculable. A supernova released as much energy as the Sun would emit over its entire 10 billion year lifetime, compressed into a few weeks of brilliant light. This was destruction on a scale never before imagined. But even as astronomers marveled at supernovae, hints of something more extreme began to emerge. In the 1960s, the Vela satellites, designed to monitor nuclear tests, detected brief flashes of gamma rays coming from space. These gamma ray bursts were unlike anything expected. They lasted only seconds, released the highest energy photons known, and came from random directions across the sky. For years, their origin was unknown. Were they from the Sun? From nearby stars? From distant galaxies? The breakthrough came in 1997, when the Italian-Dutch satellite BeppoSAX detected a gamma-ray burst, and for the first time was able to pinpoint its location accurately enough for ground-based telescopes to follow up. Within hours, astronomers found a faint, fading glow at the location, a so-called afterglow. By measuring the spectrum of this light, they determined its redshift, a measure of how much the universe had expanded since the light was emitted. The result was stunning. The burst had come from over 6 billion light-years away, halfway across the observable universe. At such distances, the energy required to produce the observed brightness was staggering. A gamma-ray burst released more energy in 10 seconds than the Sun would in its entire existence. The discovery forced a complete rethinking of what was possible in astrophysics. What could produce such power? The leading theory quickly emerged. Gamma-ray bursts were the deaths of the most massive stars, hypernovae that collapsed into black holes while simultaneously launching jets of material at nearly the speed of light. These jets, when pointed toward Earth, produced the bursts we detected. The discovery of gamma-ray bursts revealed that the universe contained events far more violent than supernovae. But the story did not end there. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected the collision of two black holes, each about 30 times the mass of the Sun, located over 1 billion light-years away. The event released more energy in gravitational waves in a fraction of a second than all the stars in the observable universe combined emitted in light during the same time. It was a new form of cosmic violence, invisible to traditional telescopes but unmistakable in its power. These discoveries, supernovae, gamma-ray bursts, black hole mergers, painted a picture of a universe far more violent than anyone had suspected. Each represented a different form of destruction, each with its own scale and mechanism. Supernovae scattered elements across space, enriching galaxies but also sterilizing nearby regions. Gamma-ray bursts concentrated unimaginable energy into narrow beams, creating zones of annihilation light-years wide. Black hole collisions reshaped spacetime itself, sending ripples across the cosmos. As astronomers studied these events more closely, patterns emerged. Gamma-ray bursts came in two types. Short bursts, lasting less than 2 seconds, were caused by colliding neutron stars. Long bursts, lasting more than 2 seconds, came from collapsing massive stars. Supernovae also showed variety. Type Ia supernovae resulted from white dwarfs exploding, while Type II came from massive stars. Each type released different amounts of energy, produced different elements, and affected their surroundings in unique ways. The discovery process was iterative. Each new observation raised new questions. How common were gamma-ray bursts? Could they threaten Earth? What happened inside a collapsing star to produce such jets? How did black holes grow so massive? Answering these questions required new instruments, new theories, and new ways of thinking. Space-based telescopes like the Hubble and Chandra observatories provided high-resolution images and spectra. Gravitational wave detectors like LIGO opened entirely new windows onto the universe. Computational simulations allowed theorists to model events too violent to recreate in any laboratory. The spark of mystery that began with ancient observations of new stars had grown into a comprehensive understanding of cosmic destruction. Yet even with all this knowledge, mysteries remained. Why did some stars produce gamma-ray bursts, while others did not? What determined the strength and duration of a burst? Could even more extreme events exist, as yet undetected? The discovery process was ongoing, each answer leading to new questions, each observation refining the picture. One of the most profound realizations was that destruction was not random or chaotic. It followed patterns, obeyed laws, and served purposes within the larger cosmic ecosystem. Supernovae enriched the interstellar medium with heavy elements, making planets and life possible. Gamma-ray bursts, though terrifying, were rare and their beams narrow, leaving most of the universe unaffected. Black holes, once formed, could stabilize at galactic centers, regulating star formation and shaping galactic evolution. Destruction, it turned out, was not the enemy of structure but its partner. The discovery of the most destructive things in the universe was also a discovery of resilience. Despite the violence, the universe persisted. Galaxies continued to form stars. Planets continued to orbit. Life, at least on Earth, thrived in a relatively quiet corner, shielded by distance and circumstance from the worst the cosmos could offer. The spark of mystery had revealed not just destruction but balance, a universe where violence and creation coexisted, where extremes were possible but not dominant. When astronomers first calculated the true energy of a gamma-ray burst, the reaction was not immediate acceptance but stunned disbelief. The numbers seemed impossible, the kind of figures that suggested an error in the calculations or a misunderstanding of the data. How could a single event, lasting only seconds, release more energy than an entire galaxy of stars? It violated intuition, challenged every expectation, and forced scientists to question whether their instruments, their methods, and their theories were truly reliable. The skepticism was understandable. Science thrives on caution, on demanding extraordinary evidence for extraordinary claims. A gamma-ray burst, releasing 10 to the 51 ergs of energy in 10 seconds, was extraordinary by any measure. To put it in perspective, that is roughly the mass energy equivalent of a few suns, completely converted to pure energy, compressed into a time frame shorter than a human breath. Nothing in the known universe suggested such events should be possible, yet the data kept pointing in that direction. Early debates centered on distance. If gamma-ray bursts were relatively nearby, within our galaxy or just beyond it, the energies would be more manageable. Still impressive, but not universe-breaking. Some astronomers favored this explanation, proposing that bursts came from neutron stars or other compact objects within the Milky Way. But the distribution of bursts across the sky argued against this. They appeared randomly in all directions, not concentrated along the plane of the galaxy where most stars and remnants reside. If they were local, they should cluster. They did not. The cosmological distance hypothesis, placing bursts billions of light years away, solved the distribution problem but created the energy problem. As more bursts were detected and their afterglows measured, the distances became undeniable. Burst after burst showed redshifts indicating they were halfway across the universe or farther. The energy calculations were not errors. They were correct, within the uncertainties of measurement. The universe did indeed produce events of such staggering power. Acceptance came gradually, not through a single revelation but through the accumulation of evidence. Each new burst with a measured distance confirmed the pattern. Theoretical models began to explain how such energies could be achieved. If a massive star collapsed into a black hole, and if that collapse produced jets of material moving at nearly the speed of light, the relativistic effects could amplify the energy enormously. The jets would be narrow, perhaps only a few degrees wide, but within those beams the energy density would be extreme. Observers in the path of the beam would see a gamma-ray burst. Those outside the beam would see nothing. This beaming model was elegant. It explained why bursts were rare in our observations, even though they might be common in the universe. Most bursts pointed away from us, invisible because we were not in their line of fire. It also explained the energy. The total energy of the explosion, summed over all directions, was still enormous, but not quite as unimaginable as the focused energy in the beam. Still, even accounting for beaming, the energies were staggering. A typical long gamma-ray burst released something like 10 to the 54 ergs total, making it the most energetic electromagnetic event since the Big Bang. Mixed with disbelief in another way. If these events were so powerful, why had we not detected them sooner? The answer lay in technology. Gamma rays do not penetrate Earth's atmosphere, so ground-based telescopes could not see them. It was only with satellites, beginning in the 1960s, that gamma rays could be detected at all. And it was only in the 1990s, with improved satellites and rapid follow-up observations, that distances could be measured. The universe had been producing gamma-ray bursts for billions of years. We had simply lacked the tools to notice. The first response was not limited to gamma-ray bursts. Black hole mergers detected by LIGO produced a similar mix of awe and disbelief. The idea that two black holes, invisible themselves, could spiral together and release more power in gravitational waves than all visible stars combined seemed absurd. Gravitational waves themselves had been theoretical for a century, predicted by Einstein but never directly observed. When LIGO announced the first detection in 2015, some skeptics wondered if it was a hoax or a glitch. But the signal was real, confirmed by multiple detectors, and the implications were profound. The response from the broader scientific community evolved quickly. Skepticism gave way to excitement as the implications became clear. These events were not just curiosities. They were windows into extreme physics, laboratories where gravity, relativity, and quantum mechanics all played roles. Gamma-ray bursts offered insights into the deaths of massive stars, the formation of black holes, and the production of heavy elements. Black hole mergers revealed the dynamics of spacetime itself, testing general relativity in regimes never before accessible. For the public, the response was equally powerful. News of gamma-ray bursts captured imaginations, sparking fears and fascination in equal measure. Could a burst aimed at Earth destroy all life? The answer was nuanced. If a burst occurred within our galaxy, and its beam pointed directly at us, the consequences would be severe. The gamma rays would strip away the ozone layer, exposing the surface to lethal solar radiation. Mass extinctions could follow, but such events are extraordinarily rare. The last gamma-ray burst in our galaxy likely occurred thousands or millions of years ago, long before humans existed. The odds of one pointing at us in the near future are vanishingly small. Still, the mere possibility added to the awe. The universe contained threats of such magnitude that distance was our only real protection. This realization was humbling. It reminded us that Earth, for all its importance to us, is a small, fragile world in a vast and indifferent cosmos. The most destructive things in the universe do not care about us. They occur according to the laws of physics, regardless of whether life exists in their paths. The first response, then, was a mixture of disbelief giving way to acceptance, skepticism yielding to evidence, and awe deepening as the implications became clear. Scientists had discovered that the universe was not the calm, orderly place it appeared to be from our vantage point. It was violent, dynamic, and capable of extremes that challenged our understanding. Each new detection, whether of a gamma-ray burst, a supernova, or a black hole merger, reinforced this truth. The cosmos contained power beyond imagination, and we had only just begun to measure it. The more astronomers learned about the most destructive events in the universe, the more contradictions emerged. On one hand, the observations were clear. Gamma-ray bursts released enormous energies. Black holes grew to billions of solar masses. Supernovae scattered elements across galaxies. The data was robust, confirmed by multiple instruments and independent teams. Yet on the other hand, the physics required to explain these events pushed theories to their limits and sometimes beyond. The contradictions were not errors but signs that our understanding, however advanced, remained incomplete. One of the central contradictions involved energy budgets. A gamma-ray burst released the equivalent of several solar masses of energy in seconds. Where did that energy come from? The collapsing core of a massive star contained gravitational potential energy, released as the core contracted. Nuclear fusion in the final moments added more. But converting these forms of energy into the focused, relativistic jets observed in gamma-ray bursts required mechanisms that were not fully understood. The jets had to be launched, accelerated, and collimated into narrow beams. Each step involved complex physics, from the formation of accretion disks around newborn black holes to the role of magnetic fields in channeling material. Theoretical models could explain parts of the process, but not all. Simulations showed that magnetic fields, twisted and amplified during collapse, could indeed launch jets, but the details depended on initial conditions, rotation rates, and magnetic field strengths, many of which were uncertain. Different models produced different predictions, and observations did not always match expectations. Some bursts were longer than predicted. Others showed spectral features that suggested additional processes at work. The contradiction was not that the models were wrong, but that they were incomplete, capturing essential features while missing others. Black holes presented their own contradictions. General relativity predicted their existence, and observations confirmed them beyond doubt. Stars orbiting the centers of galaxies moved too fast to be explained without supermassive black holes. Gravitational wave detections showed that stellar mass black holes existed and merged. Yet black holes also raised paradoxes. The singularity at the center, where density became infinite, suggested a breakdown of physics. The event horizon, where time appeared to stop for distant observers, created puzzles about information and entropy. Black holes were both perfectly described by equations and deeply mysterious in their implications. Another contradiction involved the role of black holes in destruction. They were often portrayed as cosmic monsters, consuming everything nearby. But in reality, black holes were surprisingly benign unless you approached too closely. The event horizon of a stellar mass black hole was only a few kilometers across. You could orbit safely at distances much farther than that, just as planets orbit the Sun. Even supermassive black holes, with event horizons millions of kilometers across, could be orbited without danger. The destruction came not from the hole itself, but from the environment around it, the accretion disk, the jets, the radiation. The black hole was the engine, but the real violence happened in its vicinity. Supernovae raised contradictions, time of their own. They were destructive, scattering a star across light years and releasing energy that could sterilize planets. Yet they were also creative, forging heavy elements and scattering them into space, seeding future stars and planets. Without supernovae, there would be no carbon, no oxygen, no iron. The Earth itself, and all life on it, owed its existence to the violent deaths of ancient stars. How could the same event be both destroyer and creator? The answer was that destruction and creation were not opposites but partners, two aspects of the same cosmic cycle. The contradiction extended to the question of what counted as most destructive. If you measured by energy released, gamma-ray bursts won. If you measured by the permanence of the damage, black holes were unmatched. If you measured by the volume affected, quasars, shining for millions of years and influencing entire galaxies, might claim the title. If you measured by inevitability, the heat death of the universe, where all structure eventually succumbs to entropy, was the ultimate destruction. Each measure highlighted a different phenomenon, and none could be dismissed as irrelevant. Science thrived on such contradictions. They were not failures but opportunities, signs that new physics awaited discovery. The contradictions around gamma-ray bursts spurred new models of jet formation and relativistic hydrodynamics. The paradoxes of black holes drove research into quantum gravity and the nature of spacetime. The dual nature of supernovae inspired studies of nucleosynthesis and galactic chemical evolution. Each contradiction pointed toward deeper understanding, even if that understanding remained just out of reach. There was also a philosophical contradiction. The universe, for all its violence, remained orderly. Galaxies formed, stars burned steadily, planets orbited, and life emerged. The most destructive events, though powerful, were also rare or localized. Gamma-ray bursts were terrifying, but their beams narrow and their occurrence infrequent. Black holes grew slowly, taking billions of years to consume significant amounts of matter. Supernovae enriched galaxies, but did not sterilize them entirely. The contradiction was that in a universe capable of such extremes, structure persisted, complexity arose, and beauty endured. Perhaps the deepest contradiction was between observation and intuition. Our senses evolved to navigate a human-scale world where the most destructive things were storms, volcanoes, or earthquakes. The leap from that scale to cosmic destruction required not just mathematics but imagination. Numbers like 10 to the 51 ergs did not settle into intuition. They remained abstract, symbols on a page. Yet the universe insisted they were real. Observations confirmed them. Theories explained them. The contradiction was not in the universe but in us, in the gap between what we could measure and what we could truly grasp. Science mediated this gap. It provided tools, equations, models, and analogies that allowed us to reason about the unreasonable. It turned contradiction into questions and questions into research. The mystery of gamma-ray bursts became a field of study, employing thousands of scientists across decades. The paradoxes of black holes became some of the most active areas in theoretical physics. The dual nature of supernovae became a window into cosmic evolution. Contradiction, far from being a weakness, was the engine that drove discovery. As we sat with these contradictions, we saw that they were not problems to be solved quickly, but puzzles to be lived with, explored, and gradually unravelled. The universe did not owe us easy answers. It presented phenomena on its own terms, and our task was to listen, to observe, and to piece together understanding from fragments of light, gravity, and mathematics. The contradictions remained, but they no longer felt like obstacles. They felt like invitations. When faced with the question of what is most destructive in the universe, scientists do not speak with one voice. They propose theories, build models, and debate interpretations, each bringing different perspectives to the same observations. The result is not confusion but richness, a tapestry of ideas that together approach truth more closely than any single thread could. The theories divide not because scientists disagree on the facts, but because the question itself branches into many paths, each worth exploring. The first camp focuses on energy. By this measure, gamma-ray bursts are unmatched. In 10 seconds, they release more energy than the Sun will in its entire 10 billion year lifetime. The mechanism is well understood in broad strokes. A massive star collapses, forming a black hole. An accretion disk forms around it, feeding material inward. Magnetic fields twist and amplify, launching jets of material at nearly the speed of light. When these jets punch through the stellar envelope and reach open space, they shine as gamma-ray bursts, beacons visible across billions of light years. But not all scientists agree that energy alone defines destruction. Another camp emphasizes permanence. Black holes, by this measure, are the ultimate destroyers. They trap everything that falls past their event horizons. Not just matter, but light, information, even the fabric of space-time itself seems to end at the singularity. Nothing escapes. In this view, black holes represent absolute destruction, a one-way process from which there is no return. Supernovae scatter matter. Gamma-ray bursts radiate energy, but black holes erase. A third group points to reach. Quasars, powered by supermassive black holes, shine for millions of years, influencing entire galaxies. They regulate star formation, heat the intergalactic medium, and drive winds that sweep gas out of galaxies entirely. A single quasar can affect a volume of space thousands of light years across, shaping the evolution of millions of stars. By This measure, quasars are more destructive than gamma-ray bursts, which, for all their power, last only seconds and affect only narrow beams. Then there are those who think on even larger scales. The expansion of the universe, driven by dark energy, will eventually tear apart every structure. Galaxies will drift beyond each other's horizons. Stars will exhaust their fuel. Black holes will evaporate through Hawking radiation. In the far future, the universe will be cold, dark, and empty, every trace of structure erased by entropy. This heat death is the ultimate destruction, inevitable and absolute, affecting not just regions of space, but the cosmos itself. Each theory has merits. Energy makes gamma-ray bursts the most violent short-term events. Permanence makes black holes the most absolute. Reach makes quasars the most influential. Inevitability makes cosmic expansion the most comprehensive. The theories do not contradict each other so much as highlight different aspects of destruction. Choosing among them requires deciding what destruction means, and that decision is as much philosophical as scientific. Within each camp, further divisions arise. Among those who favour gamma-ray bursts, some emphasise long bursts from collapsing stars, while others point to short bursts from merging neutron stars. Long bursts are more energetic, but short bursts may be more common. Which is more destructive? Among those who favour black holes, some focus on stellar mass holes formed from supernovae, while others emphasise supermassive holes at galactic centres. Stellar mass holes are numerous, but supermassive holes dominate their environments for billions of years. The debate extends to mechanisms. How do gamma-ray burst jets form? The leading model invokes magnetic fields, but the details remain uncertain. Some simulations suggest that jets are launched by the Blandford-Znajek mechanism, extracting rotational energy from the black hole itself. Others propose that the accretion disk plays a larger role, with magnetic fields wound up by differential rotation. Both models work, but neither fully explains all observations. The theories divide because the physics is complex, operating in regimes where general relativity, magnetohydrodynamics, and nuclear physics all matter equally. Black holes, too, spark theoretical divisions. Do singularities really exist, or do quantum effects prevent them? General relativity predicts singularities, but quantum mechanics suggests they may be avoided. Loop quantum gravity, string theory, and other approaches offer alternatives where collapse halts before reaching infinite density. If singularities do not exist, then black holes may not be quite as absolute as previously thought. The theory divides between those who trust classical relativity and those who insist quantum gravity must be considered. There are also pragmatic divisions. Some scientists study the most destructive things because they want to understand threats to Earth. Could a nearby gamma-ray burst cause mass extinction? The answer depends on distance and orientation, but the possibility is real. Others study these phenomena to test fundamental physics. Gamma-ray bursts probe relativistic jets. Black hole mergers test general relativity. Supernovae reveal nucleosynthesis. The motivation shapes the questions asked and the theories developed. Another division lies in observational versus theoretical approaches. Observers focus on what can be measured, cataloguing gamma-ray bursts, detecting gravitational waves, and imaging black hole shadows. Theorists build models to explain these observations, often predicting new phenomena before they are detected. The two approaches are complementary, but they sometimes lead to different emphases. Observers may prioritize phenomena that are detectable, while theorists explore extremes that may be impossible to observe directly. The theories also reflect cultural and intellectual traditions. Some scientists prefer elegant, simple models that explain the most with the least. Others embrace complexity, arguing that the universe is under no obligation to be simple. Some favor conservative approaches, building on established physics. Others push into speculative territory, proposing exotic mechanisms like naked singularities, wormholes, or even connections to other universes. Each tradition contributes, and the interplay between them drives progress. Despite these divisions, there is consensus on the essentials. Gamma-ray bursts are real and immensely energetic. Black holes exist and trap matter beyond recovery. Supernovae enrich galaxies. Quasars shape galactic evolution. The expansion of the universe will continue. The theories divide on interpretation, emphasis, and implications, but they agree on the phenomena themselves. This consensus provides a foundation, a shared starting point from which different paths diverge. The division of minds is not a weakness, but a strength. It ensures that no single perspective dominates, that all possibilities are explored. Science advances not through uniformity, but through diversity, through the productive tension between competing ideas. The question of what is most destructive in the universe may never have a single answer, but the attempt to answer it reveals the richness of the cosmos and the creativity of those who study it. To understand the most destructive things in the universe, observation alone is not enough. Scientists must investigate, not just by pointing telescopes, but by building instruments, developing theories, conducting simulations, and analyzing data. The pursuit of understanding cosmic destruction spans decades and involves thousands of researchers across many disciplines, from astronomers and physicists to computer scientists and engineers. It is a collective effort, driven by curiosity and the desire to know what the universe is truly capable of. The investigation begins with detection. Gamma-ray bursts, for example, cannot be predicted. They occur without warning, in random directions, lasting only seconds. To study them, satellites must be on constant watch, scanning the entire sky for sudden flashes of gamma rays. The first dedicated mission was the Compton Gamma Ray Observatory, launched in 1991. It detected hundreds of bursts, confirming their cosmic distribution and energies. Later missions, like Swift and Fermi, improved on this, detecting bursts and rapidly alerting ground-based telescopes to observe the fading afterglows. This rapid response is crucial. A gamma-ray burst's afterglow fades within hours or days, so telescopes must slew quickly to the location. Networks of robotic telescopes, operated around the world, respond automatically to satellite alerts. Within minutes, they are imaging the burst site, measuring its brightness and spectrum. These observations provide the redshift, the key to determining distance and, from that, the energy released. Each burst adds to the catalogue, refining statistical patterns and revealing diversity within the population. For black holes, investigation requires different tools. Stellar mass black holes are often found in binary systems, where their gravity pulls material from a companion star. This material forms an accretion disk, heating up and emitting X-rays. Satellites like Chandra and XMM Newton detect these X-rays, allowing astronomers to map black hole systems across the galaxy. Supermassive black holes at galactic centers are studied through the motion of nearby stars. By tracking stars orbiting the center of the Milky Way, for instance, astronomers inferred the mass of Sagittarius A star, confirming it as a black hole with over 4 million solar masses. Gravitational waves opened a new avenue. LIGO and Virgo detect the ripples in spacetime produced when black holes or neutron stars merge. The first detection in 2015 was a proof of concept. Since then, dozens of mergers have been observed, revealing the masses, spins, and distances of the colliding objects. Each detection is also a test of general relativity, confirming that gravity behaves as Einstein predicted, even in the most extreme conditions. The investigation through gravitational waves is still young, but it has already transformed our understanding of black holes. Supernovae are investigated through surveys that monitor thousands of galaxies, looking for stars that brighten suddenly. Automated systems flag candidates, and follow-up observations determine their type, distance, and energy. Some surveys, like the Zwicky Transient Facility, scan the entire visible sky every few nights. Others, like the upcoming Vera Rubin Observatory, will go even deeper, detecting millions of transient events per year. The sheer volume of data requires sophisticated software to analyze, classify, and prioritize targets for detailed study. Theoretical investigation complements observation. Computational simulations allow scientists to model events that cannot be recreated in laboratories. A collapsing massive star, for instance, can be simulated on supercomputers, solving the equations of hydrodynamics, nuclear physics, and gravity simultaneously. These simulations reveal how jets form, how shock waves propagate, and how elements are synthesized. They also predict observational signatures, guiding what to look for in data. The interplay between theory and observation is iterative, each informing the other. One of the challenges in investigation is the rarity of the most extreme events. Gamma-ray bursts in our galaxy occur perhaps once every few 100,000 years. Supermassive black hole mergers are even rarer. Waiting for one to happen nearby is impractical. Instead, astronomers survey vast volumes of space, observing thousands or millions of galaxies, increasing the odds that something interesting will happen within view. Events are distant, requiring powerful instruments to detect and analyze. Another challenge is multi-wavelength observation. A gamma-ray burst emits gamma rays, but its afterglow shines in X-rays, optical light, and radio waves. Each wavelength reveals different information. X-rays trace the shock as it interacts with surrounding material. Optical light provides the redshift and host galaxy. Radio waves reveal the expansion of the afterglow over weeks or months. Coordinating observations across all these wavelengths requires collaboration among many observatories, each with its own schedule and capabilities. The investigation also involves archival research. Not all discoveries happen in real time. Sometimes, patterns emerge only when decades of data are combined and reanalyzed. The archive of supernova observations, for instance, has been used to trace the history of star formation across cosmic time. By comparing supernova rates in distant galaxies to those nearby, astronomers infer how star formation has evolved since the early universe. Each supernova is a data point, and collectively they tell a story about galactic evolution. Spectroscopy is another critical tool. By spreading light into its component colors, astronomers can identify elements, measure velocities, and determine temperatures. A supernova's spectrum reveals which elements it ejected and at what speeds. A quasar's spectrum shows emission lines from hot gas near the black hole and absorption lines from intervening gas clouds. Each feature is a clue, and piecing them together requires both meticulous measurement and careful interpretation. Collaboration is essential. No single scientist or institution can investigate cosmic destruction alone. Telescopes are shared resources, allocated through competitive proposals. Data is published and made available to the community, allowing others to verify results and build on them. Share findings and debate interpretations. The pursuit of understanding is collective, with individuals contributing specialized expertise to a larger mosaic. The investigation is also driven by technological progress. Each generation of instruments reveals phenomena invisible to the last. Early gamma-ray detectors could barely locate bursts. Modern satellites pinpoint them within seconds. Early gravitational wave detectors struggled to reach the sensitivity needed for detections. Upgraded versions now detect mergers weakly. Each improvement opens new questions and extends the reach of investigation. As the investigation continues, the picture becomes clearer, but also more complex. Gamma-ray bursts come in multiple types. Black holes show unexpected diversity. Supernovae include rare subclasses. The universe is not tidy. It produces phenomena in gradations, with boundaries between categories often blurred. The pursuit of understanding embraces this complexity, seeking not just to catalogue, but to comprehend the processes, the physics, and the connections. The data that defines cosmic destruction arrives not as complete narratives, but as fragments, scattered observations that must be pieced together like a cosmic puzzle. Each gamma-ray burst, each supernova, each black hole merger leaves behind traces, signals encoded in light, gravity, and particles. From these clues, astronomers reconstruct events of unimaginable violence, measuring energies, distances, and timescales with precision that would have seemed impossible only decades ago. For gamma-ray bursts, the key data begins with detection. The Swift satellite, for example, detects roughly 100 bursts per year. Each detection triggers an automatic alert, broadcast to observatories worldwide within seconds. The alert includes the burst's position on the sky, its duration, and its energy spectrum. Ground-based telescopes slew to the position, searching for the afterglow. Within minutes, optical light is detected, fading rapidly. Spectra are taken, revealing absorption and emission lines that encode the redshift. The redshift is critical. It tells how much the universe has expanded since the light was emitted, and from that, the distance can be calculated. For a burst at redshift 2, for example, the light has travelled for about 10 billion years, crossing more than half the observable universe. Knowing the distance and the observed brightness, astronomers calculate the intrinsic luminosity, the total energy emitted. The numbers are staggering. A typical long gamma-ray burst releases 10 to the 51 ergs in gamma rays alone, with even more energy in the associated supernova. The data also includes temporal structure. Gamma-ray bursts are not smooth flashes but complex, flickering events. The light curve, a plot of brightness versus time, shows spikes and valleys, each lasting fractions of a second. These fluctuations reveal the inner workings of the jet, the turbulence, the stop, shocks, the variable accretion onto the black hole. Some bursts show a single peak, others show dozens. Each pattern is a fingerprint, unique but part of a larger family. Afterglows provide additional data. As the jet slams into surrounding material, it creates a shock wave that radiates across the electromagnetic spectrum. X-rays dominate initially, followed by optical and then radio emission as the shock slows and cools. By monitoring the afterglow over days and weeks, astronomers trace the expansion and measure the density of the surrounding medium. Some bursts occur in dense star-forming regions, others in sparse intergalactic space. Each environment leaves its mark on the data. For black holes, the data comes from different sources. Stellar mass black holes in binary systems emit X-rays as they accrete material. The X-ray spectrum reveals the temperature of the inner accretion disk, which in turn constrains the black hole's mass and spin. Variability in the X-rays, flickering on millisecond timescales, reflects the chaotic dance of material spiraling inward. Each flicker is a probe of the region just outside the event horizon, where general relativity dominates and space-time is sharply curved. Supermassive black holes are studied through the motion of stars. At the center of the Milky Way, stars orbit Sagittarius A star in elliptical paths, completing orbits in as little as 16 years. By tracking these orbits with exquisite precision, astronomers measure the black hole's mass, 4.1 million times that of the Sun, confined within a region smaller than the solar system. The data is unambiguous. Only a black hole can pack so much mass into so small a space. Gravitational waves provide yet another form of data. When two black holes merge, they emit waves that stretch and squeeze space-time as they pass. LIGO and Virgo detect these waves as tiny shifts in the lengths of their laser arms, smaller than 1,000th the width of a proton. The waveform, the pattern of the signal over time, encodes the masses, spins, and distance of the merging black holes. From a single detection lasting less than a second, astronomers extract a wealth of information. The first detection, GW150914, came from two black holes, 29 and 36 solar masses, colliding 1.3 billion light-years away. The merged black hole had a mass of 62 solar masses. 3 solar masses were converted to gravitational wave energy, radiated away in a fraction of a second. The peak power exceeded all the stars in the observable universe combined. The data was clean, matching theoretical predictions with remarkable precision. Supernova data comes from photometry and spectroscopy. As a star explodes, its brightness rises over days, peaks, and then fades over weeks or months. The light curve shape depends on the explosion energy, the mass ejected, and the radioactive elements produced. Spectroscopy reveals which elements are present. Type Ia supernovae show silicon and lack hydrogen. Type 2 show hydrogen lines. Each type follows a characteristic pattern, allowing astronomers to classify even distant events based on a few observations. Distance measurements tie everything together. For nearby events, parallax or standard distance indicators, like Cepheid variables, provide accurate measurements. For distant events, redshift is the primary tool. But redshift alone does not give distance directly. It requires a cosmological model, assumptions about how the universe has expanded over time. The data from supernovae, in fact, played a key role in discovering that the expansion is accelerating, driven by dark energy. This discovery earned the Nobel Prize in 2011. The data also reveals diversity. Not all gamma-ray bursts are alike. Long bursts, lasting more than 2 seconds, come from collapsing massive stars. Short bursts, lasting less than 2 seconds, come from merging neutron stars. Within each category, there is variation. Some long bursts are ultra-long, lasting thousands of seconds. Some short bursts have extended X-ray emission. Each variant requires explanation, refinement of models, and additional observations. Black holes show diversity too. Some are born spinning rapidly, others slowly. Some grow through accretion, others through mergers. Supermassive black holes range from millions to billions of solar masses. The heaviest known, in the galaxy Holmberg 15A, may exceed 40 billion solar masses. Each measurement adds to the picture, revealing the range of outcomes that nature permits. Supernovae also vary. Type Ia come from white dwarfs, but show differences in brightness and spectrum. Type 2 depend on the mass and structure of the progenitor star. Hypernovae, the most energetic, may reach energies of 10 to the 52 ergs, overlapping with gamma-ray bursts. Some supernovae, called superluminous, shine even brighter, their power source still debated. The data is fragmentary but abundant. Each year brings hundreds of new supernovae, dozens of gamma-ray bursts, and numerous gravitational wave detections. Each adds a point to the distribution, refining statistics, testing models, and occasionally surprising scientists with something unexpected. The pursuit of understanding is data-driven, grounded in measurement, and constantly evolving as new instruments come online. Beneath the surface of every measurement, every observation, every calculation about cosmic destruction lies a deeper mystery. The most destructive things in the universe are not aberrations or accidents. They are essential processes, woven into the fabric of cosmic evolution. Without them, the universe would be simpler, quieter, and ultimately lifeless. The hidden truth is that destruction is the engine of creation, the force that transforms simple into complex, that scatters seeds and clears ground for new growth. Consider gamma-ray bursts. They are terrifying in their violence, capable of sterilizing entire regions of space. But they are also rare, and their beams are narrow. For every planet caught in the path of a burst, countless others remain untouched, and the bursts themselves mark the deaths of massive stars, the very stars that forged heavy elements in their cores. When the star collapses and the burst erupts, those elements are scattered, enriching the interstellar medium with carbon, oxygen, silicon, iron. These are the building blocks of planets and life. Without gamma-ray bursts, without the supernovae that often accompany them, the universe would contain only hydrogen and helium, the primordial elements from the Big Bang. There would be no rocky planets, no water, no organic molecules. The complexity we see around us, the diversity of worlds and the possibility of life all depend on stellar deaths. Destruction, in this sense, is not the opposite of creation, but its prerequisite. The hidden truth is that annihilation and genesis are two faces of the same process. Black holes reveal another aspect of this mystery. They are often portrayed as purely destructive, consuming everything without return. But at galactic centers, black holes play regulatory roles. As they accrete material, they emit radiation and drive winds that heat the surrounding gas. This heating prevents the gas from cooling and collapsing to form new stars too quickly. Without this feedback, galaxies would exhaust their gas reservoirs in a fraction of their current lifetimes, forming stars so rapidly that they would burn out quickly, leaving behind dead galaxies. Instead, the black hole moderates star formation, ensuring a steady supply over billions of years. It sculpts the galaxy, clearing out the central regions, shaping the distribution of stars and gas. In this way, black holes are not just destroyers but architects, shaping galactic structure and evolution. The hidden truth is that their destructive power is also a creative force, a regulator that maintains balance and allows galaxies to persist. Supernovae embody the paradox most directly. They destroy the stars that produce them, scattering stellar material across light years. But that scattering enriches the interstellar medium, raising the metallicity of gas clouds, making them capable of forming new stars with planetary systems. The Sun and Earth would not exist without the supernovae that preceded them. The hidden truth is that our existence is built on the ashes of dead stars, that every atom in our bodies was once part of a star that died violently. There is also a hidden truth about energy. The universe began with enormous energy density in the Big Bang, and that energy has been transforming ever since. Stars convert gravitational energy into light. Supernovae convert nuclear energy into kinetic energy. Black holes convert mass into gravitational waves. Each transformation is irreversible, in detail, a one-way flow toward higher entropy. But locally, temporarily, structures arise, galaxies form, stars ignite, planets coalesce, life emerges. Destruction at one level enables creation at another. Another hidden truth is about information. Black holes seem to destroy information, violating the principles of quantum mechanics. But recent research suggests that information may be preserved, encoded on the event horizon, or released gradually through Hawking radiation. If true, this means that even the most absolute form of destruction is not truly final. Information persists, transformed perhaps, but not erased. The universe conserves what seems lost, ensuring that the story continues even when individual chapters end. The hidden truth also extends to time. Destruction unfolds across vast timescales. A gamma-ray burst lasts seconds, but its effects propagate for millennia. A supernova fades in weeks, but the elements it scatters drift for millions of years before joining new stars. Black holes grow over billions of years, shaping galaxies across cosmic epochs. The immediacy of destruction, its violence and suddenness, contrasts with the long, slow work of creation that follows. The hidden truth is that time mediates the transformation, allowing what seems instantaneous to have consequences that last eons. There is also a hidden truth about rarity. The most destructive events are uncommon. Gamma-ray bursts occur perhaps once per day in the entire observable universe. Supermassive black hole mergers are rarer still. This rarity is essential. If gamma-ray bursts happened constantly, if supernovae were common, if black hole mergers dominated, the universe would be chaotic, unstable, hostile to structure. Instead, destruction is calibrated, occurring frequently enough to drive evolution but not so often as to prevent it. The hidden truth is that balance matters, that the universe permits extremes but does not indulge in excess. The deeper mystery is also about perspective. From a human viewpoint, destruction is tragic, final, a loss. But from a cosmic viewpoint, It is neutral, a process, a transformation. The star does not die tragically. It completes its life cycle, returning material to the galaxy. The black hole does not consume maliciously. It follows the laws of gravity, shaping space-time according to its mass. The hidden truth is that the universe is indifferent, neither kind nor cruel, simply following the rules encoded in its structure. And yet, within this indifference, beauty arises. The nebulae formed by supernovae glow with intricate structures, filaments and shells shaped by shock waves. The jets from black holes carve cavities in the intergalactic medium, creating voids light years across. Gamma-ray bursts, for all their terror, are also beacons, visible across the universe, marking the formation of new black holes and the recycling of matter. The hidden truth is that destruction produces beauty, not despite its violence, but because of it. For much of history, humans viewed destruction as purely negative, as loss, as the end of things. It was something to be feared, avoided, mourned. But as our understanding of the universe deepened, a paradigm shift occurred. Destruction was revealed not as the enemy of existence, but as its partner, not as an ending, but as a transformation. This shift did not happen all at once. It emerged gradually, through observations that forced scientists to rethink their assumptions, to see violence not as chaos but as process, not as failure but as necessity. The turning point began with the realization that heavy elements, the building blocks of planets and life, could only be forged in stars. Early in the 20th century, when nuclear physics was still young, scientists wondered where elements heavier than hydrogen and helium came from. The answer, worked out over decades, was stellar nucleosynthesis. In the cores of stars, hydrogen fuses into helium, helium into carbon, carbon into oxygen, and so on, building heavier elements step by step. But this process only occurs at high temperatures and pressures, conditions found only in stars. The final step, the scattering of those elements into space, required destruction. A star could forge iron in its core, but unless the star died violently, those elements would remain locked inside. Supernovae provided the mechanism. When a massive star collapsed, the resulting explosion scattered its enriched core across light years, mixing it with the interstellar medium. Later generations of stars formed from this enriched gas, inheriting the elements produced by their predecessors. Without destruction, there would be no chemical evolution, no planets, no life. This realization was the first part of the paradigm shift. Destruction was not merely tolerated but required. The violence of supernovae was not incidental but essential. Without it, the universe would remain frozen in its primordial state, simple and sterile. The shift was from viewing destruction as a flaw in the cosmos to recognizing it as a feature, a mechanism by which complexity arose. The second part of the shift came with the discovery of black holes and their roles in galaxies. Initially, black holes were seen as endpoints, places where matter and information vanished forever. They were ultimate destroyers, consuming without return. But observations of active galactic nuclei, quasars, and galactic centers revealed a different picture. Black holes were not passive consumers but active shapers. As they accreted material, they emitted enormous amounts of energy, far more than nuclear fusion could produce. This energy heated surrounding gas, drove winds, and regulated star formation. Galaxies with active black holes evolved differently from those without. The black hole's influence extended far beyond the event horizon, affecting the entire galaxy. It prevented runaway star formation, cleared gas from central regions, and influenced the merger history of the galaxy. The paradigm shift was recognizing that black holes, despite their destructive nature, were integral to galactic structure and evolution. They were not flaws but features, not endings but ongoing processes. The third part came with gamma-ray bursts, and the realization that even the most violent events serve purposes. Bursts marked the deaths of the most massive stars, the formation of new black holes, and the recycling of matter on cosmic scales. Their jets, though narrow, probed the interstellar and intergalactic medium, ionizing gas and triggering secondary processes. Their afterglows provided laboratories for studying high-energy physics, relativity, and cosmology. The paradigm shift was seeing bursts not as random catastrophes, but as integral parts of cosmic machinery. This shift was not just scientific but philosophical. It required letting go of the idea that the universe should be gentle, that violence was a mistake or an imperfection. Instead, the universe operated on its own terms, indifferent to human values but consistent in its laws. Destruction was not punishment or tragedy. It was transformation, the way matter and energy flowed from one state to another, the way structure arose, persisted, and eventually gave way to new forms. The shift also affected how scientists framed their questions. Instead of asking why destruction happened, they asked how it contributed to cosmic evolution. Instead of viewing gamma-ray bursts as threats, they studied them as probes of distant galaxies. Instead of fearing black holes, they used them to test general relativity. The change was from seeing these phenomena as problems to recognizing them as opportunities, windows into physics that could not be accessed any other way. One of the clearest expressions of the paradigm shift came from the study of supernova remnants. These expanding shells of gas, lit by shock waves and radioactive decay, are among the most beautiful objects in the sky. The Crab Nebula, the Veil Nebula, Cassiopeia A, each is the remains of a supernova, a violent death transformed into a glowing monument. Within these remnants, astronomers find heavy elements, neutron stars, and evidence of particle acceleration. What began as destruction ends as creation, as the remnants seed new star formation and enrich the galaxy. The paradigm shift was also personal for many scientists. Early in their careers, they might have been drawn to the beauty of galaxies or the elegance of equations. But as they studied cosmic destruction, they saw that beauty and elegance emerged from violence, that the very structures they admired were products of processes that seemed at first glance to be purely destructive. This deepened their appreciation, revealing layers of complexity and interconnection that pure creation could not provide. The shift extended to public communication. Instead of emphasizing the dangers of gamma-ray bursts or black holes, scientists began to highlight their roles in making the universe interesting. Yes, a burst could sterilize a planet, but bursts were rare and their beams narrow. Yes, black holes consumed matter, but they also regulated galaxies and produced some of the most energetic phenomena known. The narrative changed from fear to fascination, from danger to wonder. This paradigm shift is ongoing. Each new discovery, whether of a superluminous supernova, a gravitational wave from a black hole merger, or a gamma-ray burst from the edge of the universe, reinforces the idea that destruction is not the opposite of creation but its complement. The two are inseparable, woven together in the fabric of cosmic evolution. The universe creates by destroying, builds by tearing down, and renews by scattering what was concentrated. When a gamma-ray burst erupts, when a supernova explodes, when two black holes collide, the consequences ripple outward immediately, reshaping the space around these events in ways both visible and invisible. These are not isolated incidents but catalysts, triggering chains of effects that propagate across light years and persist for millennia. The immediate ripple is where destruction becomes most tangible, where energy transforms into motion, heat, light, and the raw force that sculpts cosmic structure. Consider first the immediate aftermath of a gamma-ray burst. The jet, travelling at 99.9% the speed of light, punches through the stellar envelope and reaches open space. As it expands, it sweeps up material from the interstellar medium, creating a shock wave. This shock accelerates particles to enormous energies, producing the afterglow that fades over hours and days. The region around the burst is bathed in radiation, gamma rays, and X-rays intense enough to ionize atoms across hundreds of light years. Any planet within a few thousand light-years and in the path of the beam faces catastrophic consequences. The gamma rays arrive first, travelling at light speed, stripping away the ozone layer within seconds. Without this protective shield, ultraviolet radiation from the planet's star floods the surface, destroying DNA and sterilizing exposed life. The atmosphere itself begins to change, nitrogen and oxygen combining to form nitrogen oxides, creating a brown haze that could persist for years. Photosynthesis halts. Food chains collapse. If the burst is close enough and intense enough, the surface of the planet becomes uninhabitable, but the immediate ripple extends beyond biological destruction. The radiation ionizes the interstellar medium, creating cavities of hot, low-density gas. These cavities can persist for thousands of years, influencing how gas flows through the galaxy, where new stars form, and how matter distributes itself. In dense star-forming regions, a gamma-ray burst can trigger the collapse of nearby clouds, seeding the next generation of stars even as it sterilizes planets around existing ones. Immediate consequence is both destructive and creative, clearing and seeding in the same breath. Supernovae produce their own immediate ripples. The explosion sends a blast wave racing outward at thousands of kilometers per second, carrying the kinetic energy of the explosion. This wave sweeps up surrounding gas, compressing it into a thin, hot shell. Behind the shock, the interior is filled with tenuous, superheated plasma, glowing in X-rays. The remnant expands for thousands of years, gradually slowing as it encounters more resistance from the interstellar medium. The energy deposited by the shock wave heats the gas to millions of degrees, far hotter than any star's core. This heat drives turbulence, mixes material, and accelerates particles to relativistic speeds. Cosmic rays, high-energy protons and nuclei, stream out from the remnant, travelling across the galaxy and beyond. These cosmic rays can influence chemistry in molecular clouds, affect the ionization balance of the interstellar medium, and even impact planetary atmospheres, potentially contributing to mutation rates in living organisms over geological timescales. The immediate ripple also includes the scattering of heavy elements. A supernova ejects several solar masses of enriched material: carbon, oxygen, silicon, iron, spreading it across dozens of light years. This material mixes with the ambient gas, raising the metallicity of the region. Future stars that form from this enriched gas will have higher abundances of heavy elements, making them more likely to form rocky planets. The solar system itself formed from gas enriched by countless supernovae, each one contributing a small fraction of the elements that make up Earth and everything on it. Black hole mergers produce different but equally profound immediate consequences. When two black holes collide, they emit gravitational waves, ripples in space-time that travel at light speed. These waves carry energy, removing it from the binary and causing the orbit to decay. In the final moments, the black holes spiral together at a significant fraction of light speed, radiating enormous power in gravitational waves before merging into a single, larger black hole. The merged black hole is often disturbed, not perfectly spherical but ringing like a struck bell. This ring-down phase lasts only milliseconds, but during that time, gravitational waves continue to radiate, carrying away the remaining asymmetry. The final black hole settles into a stable state, defined by its mass and spin. If the merger occurred in a dense environment, surrounded by gas, the dynamics of the collision could produce electromagnetic signals as well, flares of X-rays or even gamma rays, though this is still debated. The immediate ripple from a black hole merger is mostly invisible in light, but profound in gravity. The waves pass through everything, stretching and squeezing space-time by infinitesimal amounts. On Earth, LIGO detects these distortions as shifts in laser arm lengths smaller than a proton. But closer to the source, the distortions would be far larger, potentially disrupting any nearby structures, though at the distances where black holes typically merge, there is little structure to disrupt. Quasars, powered by supermassive black holes, produce immediate ripples on galactic scales. The radiation from the accretion disk heats surrounding gas, driving winds that reach speeds of thousands of kilometers per second. These winds carry energy and momentum, pushing gas out of the galaxy entirely in some cases. The immediate consequence is the suppression of star formation in the central regions, clearing out the nuclear area and reshaping the galaxy's structure. The jets produced by some quasars extend for hundreds of thousands of light years, carving cavities in the intergalactic medium. These cavities, visible as voids in X-ray images, represent regions where the jet has pushed aside the hot gas that fills clusters of galaxies. The immediate ripple here is mechanical, a transfer of energy from the black hole to the surrounding medium, influencing how gas cools, how galaxies evolve, and how structure forms on the largest scales. In every case, the immediate ripple is a transfer of energy from concentrated form to dispersed, from ordered motion to random, from localized to widespread. Destruction, in this sense, is the spreading of influence, the way a single event propagates outward, touching everything in its path. The ripples fade with distance, diminishing as they expand, but their effects linger. Gas remains heated, elements remain scattered, and structures remain reshaped long after the initial event has passed. The immediate consequences are also cumulative. A galaxy experiences thousands of supernovae over its lifetime, each adding to the enrichment, each heating the interstellar medium, each accelerating cosmic rays. Dozens or hundreds of black hole mergers occur in clusters, each contributing to the gravitational wave background, each potentially influencing the dynamics of nearby systems. Gamma-ray bursts, though rarer, add their own contributions, ionizing regions and seeding star formation. Each event sends signals across the universe: light, particles, gravitational waves that carry information about the conditions at the source. Astronomers on Earth, receiving these signals billions of years later, reconstruct the events, learning about the lives and deaths of stars, the growth of black holes, the enrichment of galaxies. The immediate ripple becomes a message, a record encoded in radiation and gravity, waiting to be read. The impact of cosmic destruction extends far beyond the immediate aftermath. The echoes of these violent events ripple through time, shaping the evolution of galaxies, influencing the formation of stars and planets, and ultimately making possible the complexity we observe today. What begins as a brief explosion or collision becomes a legacy that persists for billions of years, woven into the fabric of cosmic history. The most profound impact is chemical enrichment. The universe began with hydrogen and helium, the lightest elements created in the Big Bang. Everything heavier, from carbon to uranium, was forged in stars and scattered by their deaths. Supernovae are the primary mechanism. When a massive star explodes, it ejects its enriched core into space, material that has undergone nuclear fusion at temperatures and pressures achievable nowhere else. This material drifts through the galaxy, mixing with gas clouds and raising their metallicity. Over billions of years, the average metallicity of the interstellar medium has increased. The first stars, formed from primordial gas, contained no heavy elements. They were massive, short-lived, and exploded as supernovae, enriching their surroundings. The second generation of stars formed from slightly enriched gas, allowing them to develop different properties, smaller sizes, longer lifetimes. Each subsequent generation inherited the accumulated products of earlier supernovae, increasing metallicity further. Our Sun is a third or fourth generation star formed from gas enriched by countless stellar deaths. Its metallicity, about 2% by mass in elements heavier than helium, enabled the formation of rocky planets like Earth. Without the iron core, the silicate mantle, the carbon-based molecules in the atmosphere and oceans, Earth would not exist as we know it. The impact of supernovae echoes through time, enabling not just our planet, but all the complexity that makes life possible. Gamma-ray bursts contribute to this enrichment as well, though in more localized ways. The massive stars that produce bursts also produce heavy elements, scattering them in the supernova that accompanies the burst. Additionally, some bursts may synthesize elements through rapid neutron capture, producing heavy elements like gold and platinum in small amounts. The impact is less widespread than supernovae, but still significant in the regions immediately surrounding the burst. Neutron star mergers add another dimension. When two neutron stars collide, they produce a kilonova, an explosion powered by radioactive decay of freshly synthesized heavy elements. These mergers are the primary sources of elements heavier than iron, including gold, platinum, and uranium. The impact on galactic chemistry is subtle but measurable. The abundance of these elements in the solar system, in Earth's crust and core, traces back to neutron star mergers that occurred billions of years ago. The impact also includes the regulation of star formation. Supernovae heat the interstellar medium, injecting energy that prevents gas from cooling and collapsing too quickly. Without this feedback, galaxies would form stars too rapidly, exhausting their gas reservoirs in a fraction of their current ages. Instead, the heating from supernovae moderates the process, spreading star formation over billions of years and ensuring a steady supply of new stars. Black holes at galactic centers play similar regulatory roles. As they accrete material and emit radiation, they heat the surrounding gas, preventing it from falling inward and forming stars in the central regions. This creates the observed correlation between black hole mass and galactic properties, suggesting that black holes and galaxies co-evolve, each influencing the other's growth. The impact of black hole activity echoes through galactic history, shaping not just individual galaxies, but the entire population. The impact also includes the creation of structure. Supernova shock waves compress gas clouds, triggering gravitational collapse and star formation. Entire clusters of stars can form in the wake of a single supernova, their births prompted by the death of an earlier star. The Orion Nebula, for instance, contains young stars forming in gas, compressed by previous generations of supernovae. The impact is not just destructive, but generative, clearing space while simultaneously creating conditions for new growth. Cosmic rays, accelerated by supernova remnants, have their own impact. These high-energy particles travel across the galaxy, ionizing the interstellar medium and affecting the chemistry of molecular clouds. In dense clouds where stars form, cosmic rays can penetrate deeper than ultraviolet light, influencing the ionization balance and the formation of molecules. Some theories suggest that cosmic rays may even affect planetary atmospheres, contributing to mutation rates and influencing the pace of biological evolution over geological timescales. The impact of gravitational waves is more subtle but equally profound. Each black hole merger removes energy from the binary system, converting it to gravitational waves that propagate across the universe. Over time, these waves contribute to a background signal, a faint hum, of space-time vibrations from countless mergers across cosmic history. Detecting this background, a goal of future observatories, would reveal the merger history of the universe, tracing how black holes have grown and evolved since the first galaxies formed. The echoes through time also include the transfer of angular momentum. When black holes merge, the final black hole can receive a kick, a recoil velocity from the asymmetric emission of gravitational waves. This kick can eject the black hole from its host galaxy if the velocity is high enough, or displace it from the galactic center. The impact on galactic structure can be significant, affecting the dynamics of surrounding stars and altering the galaxy's evolution. Another impact is the seeding of future destruction. The remnants of supernovae, neutron stars and black holes can themselves merge billions of years later, producing new gravitational wave events and possibly gamma-ray bursts. The impact of one generation's destruction becomes the seed of the next, a cycle that has repeated countless times across the universe's history. The echoes through time also shape cosmology itself. Observations of distant supernovae revealed that the universe's expansion is accelerating, driven by dark energy. This discovery, honored with the Nobel Prize, reshaped our understanding of the universe's fate. The impact of supernovae extends beyond individual galaxies to the cosmos as a whole, providing the data that revealed one of the deepest mysteries in modern physics. The impact of cosmic destruction is not limited to the physical universe but extends to our understanding of it. Each violent event is a laboratory, a place where physics is tested under extreme conditions. Gamma-ray bursts probe relativistic jets and high-energy processes. Supernovae reveal nucleosynthesis and shock physics. Black hole mergers test general relativity in its strongest regime. The echoes through time include the growth of human knowledge, the refinement of theories, and the expansion of our cosmic perspective. As we sit with this realization, we see that the impact of destruction is not confined to moments or locations, but spreads across space and time, connecting past to present, cause to effect, violence to beauty. The echoes are everywhere, in the elements we are made of, in the stars that light the sky, in the structure of galaxies, and in the very expansion of the universe. What seemed at first to be purely destructive reveals itself as deeply creative, as the mechanism by which the universe evolves, complexifies, and gives rise to everything we know. Behind every discovery about cosmic destruction, behind every measurement of a gamma-ray burst, or detection of a black hole merger, astronomers who spent careers building instruments, analyzing data, and piecing together stories of violence that occurred billions of years ago and billions of light years away. These are the dreamers, the ones who looked at faint signals and imagined cataclysms, who turned numbers into narratives, and who devoted their lives to understanding events they would never witness directly. The study of gamma-ray bursts began with curiosity and secrecy. In the late 1960s, the United States launched the Vela satellites to monitor nuclear weapons tests, ensuring compliance with treaties banning atmospheric detonations. The satellites detected gamma-ray flashes, but they did not match the signatures of nuclear explosions. They came from space, not Earth. For years, the data remained classified, known only to a small group of scientists and military personnel. When the findings were finally published in 1973, they sparked widespread interest and confusion. What were these bursts? Where did they come from? Astronomers like Gerald Fishman and colleagues dedicated decades to answering these questions. Fishman led the team that developed the Burst and Transient Source experiment on the Compton Gamma Ray Observatory, a satellite that detected thousands of bursts in the 1990s. Each burst added to the catalogue, revealing patterns but also raising new puzzles. The work was painstaking, requiring careful calibration, data analysis, and collaboration across institutions. For every burst detected, countless hours of preparation and follow-up were required. Others focused on theory. Stan Woosley and colleagues developed models of collapsers, massive stars collapsing to form black holes while simultaneously launching jets. These models required solving complex equations of hydrodynamics, nuclear physics, and magnetohydrodynamics, often using the most powerful supercomputers available. The theoretical work complemented observations, providing frameworks to interpret the data and predictions to test with future observations. The breakthrough in determining distances came from astronomers like Srinivas Kulkarni and colleagues, who organized rapid response teams to observe gamma-ray burst afterglows with optical telescopes. When Beppo Sachs detected a burst in 1997 and provided an accurate position, ground-based telescopes swung into action within hours. The faint afterglow was detected, its spectrum measured, and the redshift determined. This single observation transformed the field, confirming that bursts were cosmological and immensely energetic. The human element includes not just the leaders but the teams, the graduate students who spent nights at telescopes, the engineers who built detectors, the programmers who wrote analysis software. Each played a role, contributing expertise to a collective effort that spanned continents and generations. The study of gamma-ray bursts became a model of international collaboration, with data shared freely and results published openly. Black hole research has its own roster of dreamers. Subramanian Chandrasekhar, in the 1930s, calculated the maximum mass a white dwarf could, sustain before collapsing further. His work laid the groundwork for understanding stellar remnants and predicting neutron stars and black holes. J. Robert Oppenheimer and colleagues later showed that sufficiently massive cores would collapse into black holes, objects from which not even light could escape. For decades, these remained theoretical curiosities. The evidence came gradually. Cygnus X1, an X-ray source discovered in the 1960s, showed variability and spectral features, suggesting a compact object orbiting a massive star. By the 1970s, the case for a black hole was strong enough that even skeptics began to accept it. The human element here includes pioneers like Riccardo Giacconi, who developed X-ray astronomy and earned the Nobel Prize for his contributions. The study of supermassive black holes at galactic centers involved patient observations over decades. Andrea Ghez and Reinhard Genzel led teams that tracked stars orbiting Sagittarius A star, the center of the Milky Way. By measuring the star's motions with exquisite precision, they inferred the mass of the central object, confirming it as a black hole. This work required developing new techniques in adaptive optics, correcting for the blurring effects of Earth's atmosphere, and analyzing data collected over many years. Their contributions earned them the Nobel Prize in 2020. The detection of gravitational waves represents another triumph of human persistence. Albert Einstein predicted gravitational waves in 1916, but he doubted they could ever be detected. Decades later, Joseph Weber attempted to detect them using resonant bar detectors, but reported no confirmed signals. The field languished until Rainer Weiss, Kip Thorne, Barry Barish, and colleagues proposed LIGO, a laser interferometer sensitive enough to detect the tiny distortions caused by passing gravitational waves. Building LIGO required solving immense technical challenges. The mirrors had to be isolated from vibrations, the lasers stabilized, the data analyzed to distinguish real signals from noise. Thousands of scientists and engineers worked on the project over decades. When the first detection occurred in 2015, it was not the work of a single genius, but a collective achievement, the culmination of a century of theory and decades of engineering. The human element also includes those who communicate these discoveries to the public. Science writers, educators, and popularizers translate technical findings into accessible narratives, ensuring that the awe and wonder of cosmic destruction reach beyond the scientific community. Carl Sagan famously said that we are made of star stuff, a poetic expression of nucleosynthesis that captured imaginations worldwide. Neil deGrasse, Tyson, Brian Cox, and others continue this tradition, bringing the universe into living rooms and classrooms. There are also the unsung contributors, the technicians who maintain telescopes, the administrators who secure funding, the librarians who archive data. Science is a collective endeavor, and every role matters. The study of the most destructive things in the universe depends on this collaboration, on the willingness of individuals to contribute their expertise to a shared goal. The human element is also personal. Many astronomers speak of childhood fascinations with the stars, of moments when they looked up and felt a connection to something larger. For some, the motivation is intellectual, a desire to solve puzzles and understand the universe. For others, it is aesthetic, an appreciation for the beauty of nebulae, galaxies, and cosmic violence. For still others, it is existential, a need to place themselves within the vastness and to understand their origins. The work itself can be isolating. Data analysis often happens alone, in front of computer screens, sifting through numbers for patterns. Observing runs at telescopes involve long nights, disrupted sleep, schedules, and the frustration of cloudy weather ruining carefully planned observations. Yet there is also camaraderie, the shared excitement when a new burst is detected, the collaborative problem-solving when unexpected results appear, the sense of being part of a larger community, united by curiosity. The human element includes moments of joy. The first time a graduate student reduces data and sees a clear signal. The realization that a theoretical prediction matches observations, the announcement of a discovery to colleagues, met with applause and questions. These moments make the long hours worthwhile, reminding researchers why they chose this path. There are also frustrations, proposals rejected, papers requiring revisions, models that do not match data. Science is iterative, and progress is rarely smooth. But the persistence of the dreamers, their willingness to try again, to refine and improve, is what drives the field forward. Each setback is a lesson, each failure a step toward eventual success. As we reflect on the human element, we see that the study of cosmic destruction is not just about phenomena, but about people, their curiosity, their collaboration, and their dedication. The universe reveals its secrets slowly, and only to those willing to listen patiently, to work together, and to dream of understanding the most violent and beautiful events in existence. In science, consensus is not automatic. Every claim is tested, every interpretation questioned, and every conclusion subjected to scrutiny. When it comes to identifying the most destructive thing in the universe, the battle for truth is vigorous, with different camps advocating for different candidates based on their priorities and definitions. This opposition is not conflict for its own sake, but the healthy skepticism that ensures ideas are robust, that evidence is solid, and that understanding deepens through debate. The first line of opposition centers on measurement. How do you quantify destruction? By energy released? Gamma-ray bursts win by this measure, releasing 10 to the 51 ergs or more in seconds. By volume affected? Quasars, shining for millions of years and influencing entire galaxies, might claim the title. By permanence? Black holes, trapping matter beyond recovery, are unmatched. Each measure favors a different phenomenon, and advocates for each argue passionately that their metric is the most meaningful. Critics of the gamma-ray burst claim point out that while the energy is enormous, the duration is brief and the beams narrow. Most of the surrounding space is unaffected. A burst might sterilize planets in its path, but it leaves most of the galaxy untouched. Is an event that lasts 10 seconds and affects a narrow cone truly more destructive than a quasar that influences billions of stars over millions of years? The debate is not settled because the answer depends on what you value: intensity or reach, immediacy or duration. Supporters of black holes as the most destructive argue that nothing escapes, not light, not information, not even the memory of what fell in. This absoluteness, they contend, makes black holes uniquely destructive. But opponents counter that black holes also regulate galaxies, preventing runaway star formation and enabling long-term stability. Is something that serves a creative role truly the most destructive? Or does destruction require pure annihilation with no redeeming features? Supernovae advocates emphasize the dual nature of these events, both destructive and creative. They scatter elements, enrich galaxies, and make life possible. But critics ask whether something that contributes so much to cosmic evolution can be called the most destructive. The term implies finality, erasure, loss. Supernovae, for all their violence, give back what they take, recycling matter rather than removing it. Does this disqualify them, or does it reveal a deeper truth about destruction in the universe? The opposition also involves technical disputes. When astronomers first measured the energies of gamma-ray bursts, some questioned the methods. Were the distances accurate? Were the energy estimates reliable? Skeptics proposed alternative explanations, suggesting that bursts might be less energetic if they occurred in denser environments or if the beaming was less efficient. Each alternative required careful testing, comparing predictions to observations, refining models. Over time, the consensus solidified, but not without vigorous debate. Black hole masses also sparked opposition. Early estimates of supermassive black hole masses varied widely, depending on the methods used. Some relied on the motion of stars, others on the dynamics of gas, still others on the properties of jets. Different techniques sometimes gave different results, leading to debates about which method was most reliable. Improved observations and better models have narrowed the uncertainties, but the process was contentious, with each team defending their approach. Gravitational wave detections faced their own skepticism. When LIGO announced the first detection in 2015, some wondered if it was a false alarm, a glitch in the data, or even a deliberate test injection. The collaboration had to demonstrate that the signal was real, that it matched theoretical predictions, and that independent analyses confirmed the result. The transparency of the process, including releasing data for others to check, helped build consensus. But initial opposition was expected and appropriate. Another form of opposition involves interpretation. What does a gamma-ray burst tell us about the universe? Some see it as evidence of the extreme violence possible under the laws of physics, a reminder of how harsh the cosmos can be. Others see it as a natural part of stellar evolution, no more alarming than the fact that stars eventually die. The interpretation shapes the narrative, and scientists with different perspectives to emphasize different aspects. There is also opposition from the theoretical side. Some theorists argue that the most destructive thing is not a specific phenomenon but a process, entropy. The second law of thermodynamics dictates that entropy always increases, meaning that ordered structures inevitably decay into disorder. By this measure, the ultimate destruction is the heat death of the universe. When all stars have burned out, all black holes evaporated, and all structure erased. This long-term perspective contrasts with the focus on immediate, violent events, but it represents a legitimate alternative viewpoint. Others propose that vacuum decay, a hypothetical process where the universe transitions to a lower energy state, could be the most destructive. If our vacuum is metastable, a random quantum fluctuation could trigger a transition, creating a bubble of true vacuum that expands at light speed, rewriting the laws of physics and destroying everything in its path. This remains speculative, with no evidence that such a transition is possible or imminent, but it illustrates how theoretical considerations can broaden the debate. The opposition also includes philosophical questions. Is destruction inherently bad, or is it neutral, simply a transformation of matter and energy? Does labeling something as most destructive imply a value judgment, or is it purely descriptive? These questions do not have scientific answers, but they influence how scientists frame their work and how the public interprets it. Debates also arise over priorities. Should research focus on the most energetic events or the most common? Gamma-ray bursts are rare, perhaps one per day in the observable universe. Supernovae are more frequent, roughly one per century per galaxy. Which deserves more attention? Funding agencies and researchers must balance these considerations, and not everyone agrees on the right balance. The battle for truth is not just about being right, but about refining, understanding. Each challenge to a claim forces its proponents to strengthen their evidence, clarify their reasoning, and address uncertainties. Each alternative explanation, even if ultimately rejected, contributes by highlighting what must be tested and what assumptions underlie conclusions. The opposition is not an obstacle but a tool, sharpening the pursuit of knowledge. Over time, some disputes resolve. The cosmological distances of gamma-ray bursts are now accepted. The existence of black holes is undisputed. The detection of gravitational waves is confirmed. But new questions always arise, ensuring that opposition remains a constant feature of the scientific landscape. What is the maximum energy a gamma-ray burst can achieve? Can black holes be more massive than currently observed? What new phenomena await discovery? The battle for truth is ongoing, and that is as it should be. Science thrives not on certainty but on questioning, not on consensus but on evidence, not on agreement but on the willingness to challenge and be challenged. The most destructive thing in the universe may never be definitively identified, but the pursuit of the answer reveals the richness of the cosmos and the rigor of the methods we use to study it. There comes a moment in learning about cosmic destruction when the scale shifts from intellectual abstraction to something deeply personal. It is the realization that these distant, violent events are not separate from our own existence but intimately connected to it. The atoms in our bodies, the elements that make up Earth, the very conditions that allow life to flourish, all trace back to processes of destruction that occurred long before the solar system formed. This awakening transforms how we see ourselves and our place in the universe. The connection begins with the elements. Hydrogen and helium, created in the Big Bang, make up most of the universe's mass. But life requires more. Carbon forms the backbone of organic molecules. Oxygen binds with hydrogen to make water. Nitrogen is essential for amino acids and DNA. Iron fills the cores of planets and flows in our blood. None of these elements existed in the early universe. They were forged in stars through nuclear fusion and scattered by supernovae. When a massive star dies, it ejects its enriched core into space. That material, carrying carbon, oxygen, nitrogen, and iron, drifts through the galaxy, mixing with hydrogen and helium in molecular clouds. Eventually, gravity pulls these clouds together, forming new stars and planetary systems. Our solar system formed from such a cloud, enriched by countless supernovae over billions of years. Every atom heavier than helium in your body was once inside a star that died violently. This is not metaphor, it is physics. The calcium in your bones was synthesized in a supernova. The iron in your blood was forged in a stellar core and scattered in an explosion. The oxygen you breathe was created by fusion and released when the star could no longer sustain itself. You are built from the debris of destruction, a mosaic of atoms whose origins lie in violence occurring billions of years ago. The awakening deepens when you consider the rarity of these processes. Not every star produces heavy elements. Only massive stars, those at least 8 times the mass of the Sun, live fast enough and die violently enough to enrich the galaxy. Smaller stars, like red dwarfs, burn slowly and never explode. Our Sun will eventually die quietly, shedding its outer layers as a planetary nebula, but leaving its core as a white dwarf. It will not contribute significantly to galactic enrichment. We owe our existence to the rare massive stars that lived briefly and died spectacularly. If the universe contained only small stars, there would be no planets like Earth. No water, no life. The destructive deaths of massive stars are not incidental to life, but essential. Composed only of the lightest elements, incapable of producing the complexity we see. This realization brings a sense of connection. You are not separate from the universe, observing it from outside. You are part of it, made of it, a product of its processes. The supernovae that scattered the elements of your body did not know they were creating the raw materials for life. They followed the laws of physics, blindly, indifferently. Yet here you are, a consequence of that indifference. Awareness arising from atoms that were once in the hearts of dying stars. The awakening also includes a recognition of safety. The most destructive things in the universe are real and powerful, but they are also distant. The nearest star capable of going supernova, Betelgeuse, is over 600 light-years away. When it eventually explodes, the light will be spectacular, visible during the day, but it will not harm Earth. Gamma-ray bursts are terrifying, but the odds of one occurring in our galaxy, pointing at us, are vanishingly small. The last such event may have occurred millions of years ago, long before humans existed. We live in a relatively quiet region of the Milky Way, far from the galactic center, where massive stars cluster and black holes dominate. Our solar system orbits in a spiral arm, a place where star formation is moderate, not frenzied. Planets orbiting stars in dense, active regions would face higher risks from supernovae, gamma-ray bursts, and radiation from nearby massive stars. Life, if it arose at all, might be repeatedly sterilized. Our existence depends on this balance, on being close enough to benefit from the enrichment provided by dying stars, but far enough to avoid their immediate dangers. The awakening is recognizing that we are protected by distance and circumstance, that the universe's violence happens elsewhere, leaving us in a pocket of calm where complexity can develop and persist. Yet the awareness is also humbling. We are not special in the cosmic sense. The universe does not care about us. The processes that made us are the same that could destroy us, indifferent to the outcome. A gamma-ray burst could occur in our galaxy tomorrow, and if its beam pointed at Earth, there would be nothing we could do to prevent the consequences. The odds are low, but they are not zero. The universe permits both creation and destruction, and we exist in the narrow window where the former has outweighed the latter. This awareness changes how we see the night sky. Each star is a furnace, burning fuel, building elements, and eventually dying. Some will explode, scattering their contents. Others will fade quietly. A few, the most massive, may produce gamma-ray bursts or collapse into black holes. The sky is not a peaceful backdrop but a dynamic, evolving arena where creation and destruction unfold continuously. We are witnesses to this process, observers, made possible by it. The awakening also brings gratitude. We did not choose to exist. We did not create the conditions that allow life. We are beneficiaries of a chain of events stretching back billions of years, a chain that includes the violent deaths of countless stars. Those deaths were not sacrifices made for our benefit. They were natural outcomes of stellar evolution. Yet without them, we would not be here. There is a strange comfort in this. We are temporary, fragile, dependent on conditions beyond our control. But we are also part of something larger, connected to the universe through the atoms we are made of and the processes that created them. The most destructive things in the universe are not our enemies but our ancestors, the sources of the elements that make life possible. The awakening is not just intellectual but emotional. It is the moment when the abstract numbers, the energies, and distances settle into a felt truth. You are stardust. You are built from the ashes of destruction. Your existence is a testament to the creative power of cosmic violence. And in recognizing this, you see that destruction is not the opposite of life, but its foundation. As we approach the end of this journey, a deeper truth emerges, one that transcends the individual phenomena we have explored. The most destructive thing in the universe may not be a specific event or object, but a principle, a reality woven into the fabric of existence itself. That principle is transformation. Nothing lasts forever. Everything changes. And in that change, in the transitions from one state to another, lies the essence of both destruction and creation. Gamma-ray bursts, supernovae, black holes, quasars, all are expressions of transformation. A massive star transforms from a shining beacon into a scattered cloud of gas and a compact remnant. A black hole transforms in falling matter into radiation and gravitational waves. A quasar transforms the energy of accretion into light that shapes galaxies. Each event is a transition, a shift from one configuration to another, and in that shift, what came before is destroyed to make way for what comes next. This is the deepest truth. Destruction is not the opposite of creation, but its partner. They are two aspects of the same process, inseparable and equally necessary. The universe does not build structures that last forever. It builds structures that exist for a time, serve a purpose, and then give way to new structures. Stars burn, explode, and scatter. Galaxies merge, evolve, and transform. Even the universe itself expands, cools, and will eventually reach a state where no new stars form and all existing structures decay. This impermanence is not a flaw but a feature. It is what allows the universe to evolve, to increase in complexity, to produce diversity. If stars did not die, their heavy elements would remain locked in cores, unavailable to form planets and life. If black holes did not grow, galaxies would evolve, differently, perhaps less stably. If supernovae did not explode, the interstellar medium would remain thin and unpolluted, incapable of forming the next generation of stars. The revelation is that what we call destruction is really recycling, transformation, the way the universe renews itself. Matter is not destroyed in the absolute sense. It changes form, shifts configuration, but persists. Energy is not lost. It radiates, dissipates, spreads, but remains conserved. Even information, according to some interpretations, is preserved, encoded in ways we do not yet fully understand. This truth applies on every scale. At the quantum level, particles appear and disappear, virtual fluctuations that borrow energy from the vacuum and return it. At the galactic level, structures merge, grow, and evolve. At the cosmic level, the universe expands, driven by dark energy, stretching space and thinning matter. Each process involves transformation, the destruction of one state to enable another. The deepest truth also includes the role of entropy. The second law of thermodynamics states that entropy, a measure of disorder, always increases in a closed system. This means that organized structures, from stars to galaxies to life itself, are temporary islands of order in a sea of increasing disorder. They exist by exporting entropy to their surroundings, maintaining local order at the cost of greater disorder elsewhere. Eventually, the balance tips and the structure decays. This is not tragic, but inevitable. Entropy is not evil. It is the natural progression of systems toward equilibrium. A star burns, converting ordered nuclear fuel into disordered radiation and heat. It maintains itself for a time, but eventually the fuel runs out, entropy wins, and the star transforms. The revelation is that this process, far from being a failure, is the mechanism by which the universe explores possibilities, creating temporary complexity within the framework of inevitable decay. The deepest truth also touches on time. Destruction unfolds across vast timescales, from the microseconds of a black hole merger to the trillions of years of cosmic expansion. Yet each moment is part of the same story, the same cycle of birth, evolution, death, and renewal. Time mediates transformation, allowing what seems permanent to reveal itself as transient, allowing what seems destructive to become creative. For humans, this truth is both sobering and liberating. Sobering because it reminds us that nothing we build will last forever. Civilizations rise and fall. Planets will eventually be consumed by their stars. Stars will die. Galaxies will disperse. Even the universe itself will one day reach a state of maximum entropy, cold and dark, with no structure remaining. Liberating because it frees us from the illusion of permanence, allowing us to appreciate the present, to value what exists now, knowing it is temporary. The revelation is also about meaning. If destruction is inevitable, does anything matter? The answer depends on perspective. From the cosmic viewpoint, nothing is permanent, and in that sense, nothing has absolute significance. But from the human viewpoint, meaning arises from the temporary, from the fact that we exist now, in this moment, made of atoms forged in stars, aware of our origins and our fate. We matter because we are here, because we can ask questions, because we can wonder. The most destructive thing in the universe, then, is not a gamma-ray burst or a black hole, but the passage of time itself, the relentless march toward entropy, the transformation that touches everything. Yet this destruction is also the source of all creation, the clearing of old to make way for new, the scattering of elements that become planets and life, the collapse that forms black holes and neutron stars, the expansion that stretches space and shapes the cosmos. The deepest truth is that destruction and creation are one, two names for the same process. To destroy is to transform. To transform is to create. The universe does not preserve but renews, does not hold but releases, does not stop but continues. And in that continuity, in that endless cycle of change, lies both the terror and the beauty of existence. As we sit with this revelation, we see that the question we began with, What is the most destructive thing in the universe does not have a single answer. It has many, depending on how we define destruction, what we value, and what timescale we consider. But perhaps the truest answer is that the most destructive thing is also the most creative, the force that makes the universe dynamic, evolving, and endlessly fascinating. It is the principle of change itself, the transformation that ensures nothing stays the same, but that everything, in changing, contributes to the larger story. As the pieces of this exploration settle into place, a quieter question emerges. What does it all mean? We have traced the most destructive forces in the universe, measured their energies, understood their mechanisms, and recognized their roles in cosmic evolution. But meaning is not found in the facts alone. It arises when we step back and ask how these phenomena relate to us, to our existence, to the universe we inhabit. One reflection is about scale. The energies released by gamma-ray bursts, supernovae, and black hole mergers dwarf anything in human experience. We cannot truly visualize 10 to the 51 ergs, or the collision of objects 30 times the mass of the Sun. These numbers remain abstract, symbols on a page, yet they describe real events, phenomena that shape galaxies and drive cosmic evolution. The reflection is that the universe operates on scales far beyond our intuition, and yet we can comprehend them, at least mathematically. This ability to understand what we cannot directly experience is remarkable. Through telescopes, we see light that travelled billions of years to reach us. Through equations, we model processes that occur at speeds and energies beyond laboratory reach. Through imagination, we bridge the gap between human scale and cosmic scale. The reflection is that science extends our awareness far beyond our senses, revealing a universe stranger and grander than we could have guessed. Another reflection is about violence and beauty. The most destructive events in the universe also produce some of the most beautiful phenomena. Supernova remnants glow with intricate structures, filaments and shells shaped by shock waves. The jets from black holes carve elegant cavities in the intergalactic medium. Gamma-ray bursts, for all their terror, mark the births of black holes and the recycling of matter. The reflection is that violence and beauty are not opposites but companions, both arising from the same underlying physics. This challenges the human tendency to categorize experiences as good or bad, beautiful or ugly. The universe does not make such distinctions. A supernova is neither good nor bad. It simply is a natural outcome of stellar evolution. Our aesthetic response, our sense of beauty or terror, is something we bring to the observation. The reflection is that meaning is not inherent in the universe but constructed by us, shaped by our values and perspectives. A third reflection is about necessity. The most destructive things in the universe are not optional or incidental. They are essential. Without supernovae, there would be no heavy elements, no planets, no life. Without black holes, galaxies would evolve differently, perhaps less stably. Without gamma-ray bursts, the universe would lack one of its most energetic processes, a probe of extreme physics. The reflection is that what seems purely destructive serves purposes, contributes to larger patterns, and enables outcomes we value. This inverts the usual narrative. Destruction is not the enemy of order, but its partner. It clears space, redistributes matter, and drives change. The universe is not a static perfection, but a dynamic process, constantly transforming, and destruction is the mechanism of that transformation. The reflection is that we live in a universe that renews itself through violence, that creates through destruction, and that balances extremes to produce the complexity we observe. Another reflection is about safety and fragility. We exist in a relatively quiet region of the galaxy, shielded by distance from the worst the universe can offer. But this safety is not guaranteed. A gamma-ray burst could occur in our galaxy. A nearby star could go supernova. An asteroid could impact Earth. The universe does not protect us out of care. We are protected by circumstance, by the low probability of catastrophic events occurring nearby. The reflection is that our existence is contingent, dependent on conditions beyond our control, and fragile in the face of cosmic forces. Yet this fragility does not diminish us. If anything, it makes our existence more precious. We are temporary arrangements of matter, aware and curious, asking questions about the universe that made us. That awareness is extraordinary, perhaps rare. The reflection is that even if we are insignificant on cosmic scales, we are significant to ourselves, and that is enough. A fifth reflection is about connection. The atoms in our bodies were forged in stars and scattered by their deaths. We are not separate from the universe, but part of it, products of the same processes we study. When we observe a supernova, we are, in a sense, observing our own origins. When we detect a gravitational wave, we are witnessing the continuation of a story that includes us. The reflection is that understanding cosmic destruction is also understanding ourselves, our place, and our heritage. This connection extends to the future. The sun will eventually die, expanding into a red giant and consuming Earth. The Milky Way will collide with Andromeda, reshaping both galaxies. The universe will continue to expand, cooling and thinning until no new stars form. But these events lie billions of years in the future, timescales so vast they are almost abstract. The reflection is that while destruction is inevitable, it is also distant, allowing us to live, build, and wonder without immediate threat. Another reflection is about perspective. From Earth, the universe appears calm. The night sky is serene, the stars unchanging over human lifetimes. Only through instruments do we detect the violence, the gamma-ray bursts, the supernovae, the black hole mergers. The reflection is that perspective shapes reality, that what seems peaceful from one viewpoint is chaotic from another, and that the universe contains both truths simultaneously. Finally, there is a reflection about meaning and purpose. The universe does not provide inherent meaning. It does not care whether we exist or what we do. But within this indifference, we create meaning. We ask questions, seek understanding, build communities, and tell stories. The most destructive things in the universe challenge us to think beyond ourselves, to appreciate the vastness, and to find significance in the temporary, the fragile, and the beautiful. The reflection is that meaning is not given but made, and in making it, we affirm our place in the cosmos. As this journey through cosmic destruction comes to a close, it is time to return gently to where we began, to the quiet night sky, to the simple act of looking up and knowing that somewhere, hidden in the vastness, the most violent forces in the universe are at work. The knowledge we have gathered, the energies and mechanisms, the atoms and echoes, all settle now into a quieter understanding, one that allows rest while holding the wonder. The legacy of cosmic destruction is written everywhere. It is in the ground beneath your feet, built from silicon, iron, and oxygen forged in stellar cores. It is in the air you breathe, nitrogen and oxygen, scattered by supernovae billions of years ago. It is in your body, carbon and calcium, hydrogen and phosphorus, all gifts from dying stars. The most destructive things in the universe left behind the raw materials of your existence. Their legacy is not abstract. It is physical, tangible, present in every atom. This legacy extends beyond the material. Cosmic destruction shapes the evolution of galaxies, regulates star formation, and drives the chemical enrichment that makes planets and life possible. Without gamma-ray bursts, supernovae, and black holes, the universe would be simpler, less diverse, less capable of producing the complexity we observe. Their legacy is the very structure of the cosmos, the distribution of matter, the abundance of elements, the conditions that allow awareness to arise. The legacy also lives in the questions they inspire. Every gamma-ray burst detected, every supernova observed, every black hole merger recorded adds to our understanding, refines our theories, and reveals new puzzles. The most destructive things in the universe are not just phenomena but teachers, laboratories where physics is tested under extreme conditions. windows into regimes we cannot recreate on Earth. Their legacy is the growth of human knowledge, the expansion of our cosmic perspective. Returning to the question that began this journey, what is the most destructive thing in the universe? We find that the answer is layered. By energy, gamma-ray bursts dominate, releasing more power in seconds than the sun will in billions of years. By permanence, black holes reign, trapping everything that crosses their horizons. By reach, quasars shape entire galaxies over millions of years. By inevitability, entropy, and cosmic expansion will eventually erase all structure. Each measure highlights a different aspect of destruction, and none can be dismissed. But perhaps the deepest answer is that the most destructive thing is transformation itself, the principle that nothing lasts, that everything changes, and that in changing, creates space for new forms. Destruction is not the opposite of creation, but its mechanism, the way the universe renews, evolves, and explores possibilities. The legacy of destruction is creation, the scattering of seeds, the clearing of ground, the transformation of simple into complex. As we close this exploration, we return also to the theme of safety. The most destructive things in the universe are real and powerful, but they are also distant. We live in a pocket of calm, shielded by the vastness of space from the worst the cosmos can offer. Gamma-ray bursts flash across the universe, but rarely in our galaxy. Supernovae explode, but the nearest capable star is hundreds of light years away. Black holes grow, but they affect only their immediate surroundings. We are spectators to cosmic violence, observers safe enough to wonder. There is comfort in this distance. The night sky, so peaceful from our vantage point, conceals ongoing violence. But that violence does not threaten us directly. We can rest beneath the stars, knowing they will continue to shine, that the processes they embody will continue to unfold, and that the universe, for all its extremes, permits islands of stability where complexity can flourish. The return is also a return to ourselves. We began by asking about destruction, about power and violence on cosmic scales, but the answer brought us back to creation, to the elements that make us, to the processes that enabled our existence, to the balance that allows life to persist. The most destructive things in the universe are not our enemies, but our origins, the sources of everything we are made of and everything we depend on. As you close your eyes tonight, you might picture a gamma-ray burst, its jets slicing through space, invisible to us but recorded by satellites. You might imagine a supernova, its shockwave expanding, scattering elements across light years. You might think of two black holes spiraling together, releasing gravitational waves that ripple through space-time. These events are happening now, somewhere in the universe, continuing the cycle of destruction and creation that has unfolded for billions of years. You might also think of the atoms in your body, once part of stars that lived and died long before the sun existed. The iron in your blood, the calcium in your bones, the oxygen in your lungs, all were forged in stellar furnaces and scattered by violence. You are stardust, a temporary arrangement of atoms brought together by chance, aware and questioning, part of the universe looking back at itself. The legacy of cosmic destruction is that you are here, alive, conscious, able to wonder. That is not a small thing. It is a consequence of billions of years of cosmic evolution, of stars living and dying, of galaxies forming and merging, of matter and energy transforming endlessly. You are a product of that process, connected to the most destructive things in the universe through the very substance you are made of. And so, as this journey ends, let the knowledge settle gently. The most destructive things in the universe are powerful beyond imagination, but they are also distant. Their violence filtered by space and time into faint signals and ancient light. They are essential, driving the processes that make complexity possible. They are beautiful, producing structures and phenomena that inspire awe, and they are connected to you through the atoms they created, the conditions they shaped, and the story they continue to tell. Rest now, beneath the stars, knowing that the universe is vast, dynamic, and filled with both creation and destruction. Know that you are safe, shielded by distance, yet part of the larger whole. The most destructive things in the universe rage in the darkness, but here, in this quiet moment, you are at peace. The cosmos continues its work, and you, made of its dust, can drift into sleep, carried by the same rhythms that shape galaxies and scatter stars. The journey is complete, but the universe remains, endlessly transforming, endlessly renewing, endlessly inviting us to wonder.